Welcome to IMAGO Tutorials. In the previous tutorial, we have shown how to remotely build, execute and debug programs on the VisionSensor PV from a Windows-based PC with Visual Studio. In this tutorial, we will show how to fully exploit the computational power of the Windows-based PC to sensibly accelerate the program's building. In particular, we are going to generate executables for the VisionSensor PV locally on the PC, through the so-called cross-compilation process. For achieving this task, we need a cross-compiler which runs on the host architecture, in our case the Windows-based PC, and which generates executables for different target architecture, the 32-bit ARM Linux-based architecture of the VisionSensor PV. First of all, let's open a browser and type gnutoolchains.com/beaglebone to reach the web page providing pre-built Windows cross-compilers for the BeagleBone board, which has a similar architecture to the VisionSensor PV. Download the latest available toolchain by clicking on the upper link on the right. Execute the downloaded file by clicking on it and follow the instructions. Here it is possible to specify the installation directory of the toolchain. Prefer paths without spaces, which is generally good for Linux. Accept the terms of the license agreement and hit install. This process takes a couple of minutes to complete. Now that the cross-compiler has been installed, we additionally require a local copy of the VisionSensor's header files and libraries to be able to locally compile programs for the VisionSensor PV. Open the directory where the BeagleBone toolchain has been installed and create a new directory which will hold a copy of remote mentioned files necessary for building. We call it sysroot. The simplest and most effective way to copy files across architectures is to launch Smarty from a Windows command line prompt. Smarty takes additional care of converting important library references, which are typical under Linux, to proper Windows-readable files. Type the following command with the chosen sysroot path and press Enter to start the cross-platform syncing. In the pop-up window, hit Select to set up an SSH connection to the VisionSensor PV. Enter the IP address of the sensor in the hostname field, a username for the login, root in our case, and the password. Then hit Connect to get back to the first window. Choose to synchronize the selected directories only as recommended. Make sure to add the directory /opt/imago technologies into the list. If needed, also include additional remote directories. Then hit Synchronize to start the synchronization process. This may take a couple of minutes to complete. Once sysroot has been successfully synchronized, the local copies of the selected remote directories appear in the Windows folders, ready to be used for cross-compilation. Before proceeding, double-check that the global path variable includes the binary directory of the toolchain where the cross-platform tools are stored. Additionally, check whether the VisionSensor PV libraries have been properly copied to the following path. For the cross-compiler to work, the following 4 libraries must exist. If any of these libraries are missing, make a manual copy of the correspondent file, for instance libhxhal32.so.1.6.6.2, and rename it properly with a .so ending. Now we are all set to cross-compile an example program. Move to the directory where the IMAGO Technologies examples are stored and enter the source folder of the fgexample_linux program. Then execute the following command. The beginning of the command is the BeagleBone C++ cross-compiler, which generates executables for ARM Linux-based architecture like the VisionSensor PV. Main.cpp is the C++ source file for which an executable will be generated. -o main indicates the output name of the executable, in this case simply main. This part specifies the location of the local sysroot required to locate header files and libraries. The option -i equals specifies a list of include directories where the header files are located. In our case, we just include the IMAGO Technologies SDK directories. The option "-l equals" specifies a list of library directories where the libraries are located. In our case, these are simply the IMAGO Technologies SDK lib directories. Next follows a list of specific libraries to be included, all of them preceded by the tag "-l". On top of the IMAGO Technologies libraries, we must explicitly include the RT, DL, and pthread libraries, which the SDK depends on. By pressing Enter, the cross-compiler executes with the provided parameters. In case of success, the compiler simply returns the command prompt. Navigate to the directory where the compiler has executed and locate the generated executable, which is main in our case. Then grab a MOBA Xterm connection to the VisionSensor PV and copy the executable to the remote directories in order to test a remote execution. From the remote shell on the sensor, run file on the executable to verify its type. The printed message should specify a 32-bit ARM executable. In that case, run the following command once on the file to make it executable under Linux. Then run it by preceding its name with /. The program should now run flawlessly. Next, print out the FG camera version and grab a single image before finishing. This first execution example demonstrates the effectiveness of a Windows-based PC compilation of Linux-based ARM executables. Let's cross-compile also the second SDK example located in the SDK subfolders. Navigate to the corresponding source directory from the Windows command line and run the same cross-compilation command to generate the ARM executable main. Upload it onto the remote VisionSensor folder, make it executable as before, and run it. The toolchain includes compilers which can interpret most of the makefile's directives. Let's demonstrate this by opening the first test_Linux examples makefile and perform some editing before passing it to the cross-compiler. First of all, we need to replace the compiler with the local C++ cross-compiler. Then we add the sysroot path in the CPP flags to allow the compiler to locate the local copy of the remote VisionSensor PV headers and libraries. Add an equals sign between -i and the include paths to make the cross-compiler understand this directive. Remove the unused directives. In particular, make sure to remove the -c, as this one prevents linking. In the LD flags, add an equals sign as before between -l and the library directories. Remove the additional VIB interface parameter, which cannot be interpreted by the cross-compiler, and complete it with the missing 32, also part of the corresponding library file name. Add all the missing library references at this location, similarly to those present in the command line we used before. Notice that when compiling remotely on the VisionSensor, only the VIB interface library is explicitly mentioned, as the others are automatically found and linked with each other internally. Instead, the cross-compiler needs the full specification of all needed libraries without exceptions. Remove echoes and sed commands, as these cannot be interpreted by the cross-compiler and would otherwise produce a reading error. Lastly, modify the makefile all directive to complete it with the missing source files, the output binary name, and the CPP flags, right before the LD flags. Then remove or comment out the last unnecessary lines until the clean directive. Press Ctrl key and S to save. Now this makefile is ready to be used by the local cross-compiler on the Windows PC to produce VisionSensor PV executables. Let's open a Windows command prompt at the makefile directory location and run make to start the building process. The output is the actual building command, which is executed after interpreting the modified makefile. Notice that this reflects the command we used before when launching cross-compilation from the command line. In case of success, no more lines are printed. Open a Windows folder at the same location to visualize the produced executable, in our case First Test Linux. Then, as before, copy the file to the remote VisionSensor PV. From the remote shell, make it executable on Linux and then run it. So far, we have demonstrated how to build VisionSensor PV programs from the Windows command line and makefile. Cross-platform building can be made much easier by using Visual GDB, a Visual Studio extension supporting cross-compilation, linking, debugging and automatic synchronization with the remote VisionSensor PV. Open a browser and type visualgdb.com/download to reach the download page of a Visual GDB trial. Hit download and once done, execute the downloaded setup file. Follow the instructions through the setup. Accept the terms in the license agreement to proceed. Choose Quick Installation to install Visual GDB fully and integrate it into all Visual Studio installations. Alternatively, Advanced Custom Installation can be selected for better control over the additions installed and the Visual Studio integrations to perform. Finally, click Install to proceed with the installation. This may take a couple of minutes. Once done, hit Finish to exit the setup. At this point, the Visual GDB extension should have been fully integrated in Visual Studio. Let's verify this by launching Visual Studio. Create a new project by navigating through the menu with File, New Project. Among the installed project types, choose Visual GDB Linux Project Wizard to create a cross-platform Linux project using Visual GDB. Click OK to confirm. Confirm the default Clang-based functionality or modify them according to your needs. For the best debugging experiences, it's necessary to choose paths without spaces. At this point, you can hit No to go back to the previous window and choose a different space-free path. In this small test, we ignore the warning and proceed by pressing Yes. Select the console application with the MS Build and click Next to proceed. Select Build the project locally with a cross-compiler and then choose the BeagleBone Debian toolchain we previously installed as the main cross toolchain to be used. Under Deployment Computer, choose Create a new SSH connection and specify the VisionSensor PV hostname with its IP address, username root and password. Then hit Create to establish a connection to the remote host. Hit Save the host key if you wish to remember this key for future use. Choose a remote location where the executables will be copied for remote execution by updating the field Deployment folder. We choose the root directory for simplicity. Click on the small blue link Synchronize Headers and Libraries to make a local copy of the VisionSensor PV headers and libraries. This opens a pop-up interface similar to the one we used earlier from the command line in SmartT. Among the directories to synchronize include /opt/imago technologies as before and any other needed library and headers directories. Then hit Synchronize to start copying the chosen files locally. This process may take a while. Once done, Visual GDB pops up a window stating that the sysroot has been synchronized locally. Close the synchronization window by pressing Close and finally hit Finish to conclude the project setup. After a brief check on the installed packages, compilers and so on, Visual GDB creates a Linux project with the wanted settings, now visible on the right-hand side of the Visual Studio window. Now let's add the required include directories and libraries for the IMAGO Technologies example program we will use for testing. Go to Project Visual GDB Project Properties and update the MS Build Settings tag. Add the following among the include directories. Then add this command among the library directories and provide the full list of libraries as we did before in the library names field. Press Apply and OK once done. Now grab a Windows folder opened at the location where the source code main.cpp of the fgexample_Linux program is located. Drag and drop it into the source files of the Visual Studio project. Remove the source file linuxproject1.cpp from the source files folder, as its main definition will otherwise collide with the one present in main.cpp. Double-click on the just copied file to visualize its content. Finally, press the Visual GDB debugger button on the top to start local building and remote execution of the example program. In case of success, the GDB server console on the bottom right shows the output of the program, which is executed remotely on the VisionSensor PV. Notice that compared to remote building, local building via cross-compilation is computationally much faster. The speed gain is noticeable even on this small example program. To conclude this tutorial, let's once more open a remote shell on the VisionSensor PV and access the location where the executable has been deployed, in our case the root directory. By refreshing the FTP browser on the left of the MobiXterm window, the deployed executable Linux Project 1 appears among the files. Double-check the file type by typing File Linux Project 1. Then execute it remotely to visualize a similar output to the Visual GDB console in Visual Studio. In this tutorial, we have shown how to perform fast building and execution of programs for the VisionSensor PV using the locally installed cross-platform toolchain on the Windows PC. We have gone through cross-platform tools for command line and makefile-based building. We have also explained how to use the convenient Visual GDB tool for integrated Visual Studio building and debugging experiences. To see more video tutorials, check out our channel. Thank you for watching.